שלום לכל הנוכחים וברוכים הבאים להרצאת קולוקיום נוספת. היום יום שני, 7 ליוני 2021, ויש לנו היום את תומר פישמן, בינתחומי, נכון? ככה זה נקרא, בינתחומי בהרצליה. אז תומר, the floor is yours. קדימה.
Thank you very much, Danny. I will do this in English. Hope that's okay with everybody. So thank you for the introduction, Danny. As you said, my name is Tomer Fishman, and I'm from the School of Sustainability at the IDC Herzliya, Bentchumi Herzliya, for the Hebrew speakers among us. Maybe just a very quick introduction about who I am. I'm a lecturer, or I guess in the Technion it's an assistant professor, and that's what it's called, in the School of Sustainability at the IDC. I've been there for almost 3 years. Before that, I did a postdoc at Yale University, and before that, I spent 8 years in Japan. No, sorry, 6 years in Japan. 8 is wishful thinking, I guess. Doing my Masters of Engineering, Environmental Engineering, and a PhD in Environmental Science. And before that, I studied economics at the Hebrew University for my undergrad degree. So it's been a bit of a mixed thing, an interesting ride so far. But since getting to Japan, I started working on the field that I'm going to present to you today. And now that you know a bit about me and how I kind of have a mixed background, that can maybe help with the topic, which is, as we see here, it's socioeconomic metabolism. That's the framework that my research revolves around. And specifically, I would like to talk with you about the weight of the city and how its materials mediate societal function and environmental impacts. Very long title, but as you can see here, I marked the weight of the city as a starting point for us. And maybe a short question to you, the weight of the city. What is the weight of the city? What's the weight of Israel's cities? By weight, I mean the mass of all of the materials that compose basically everything we see here, the buildings, roads, infrastructures, of all sorts of different types. And yes, I know I took this picture from your neighbors up the hill, from the tower, but well, you can see the Technion there, somewhere to the right. Lots of construction apparently, so the weight of the cities in Israel are growing. But how much materials do we have embedded in all of these, in all of this built environment? Turns out nobody knows. We asked around. We asked the construction industry, we asked city planners, we asked government, both local and the national government, and nobody really knows. So we started doing some calculations, and our preliminary results give us more or less these values. Around 750 million tons. We already know that this is an underestimation. The final numbers are going to be higher. We didn't count different types of infrastructure, mostly transport infrastructure. So maybe this is only for buildings. And as you can see here, it's mostly gravel, sand, and cement. That's the materials, the main materials that compose concrete, but also lots of metals. And there are other materials like glass and plastics and ceramics, but they are much smaller compared to these main construction materials. These are also the structural ones, the ones that are actually important to make sure that buildings and infrastructure will don't fall down. But this is what we're interested in, understanding how much material is out there in the built environment or building up the built environment. We're mostly interested in these types of materials, mostly minerals, which include cement, aggregate, sand, asphalt, and so forth. Biomass, mostly timber, which can be used as a construction material. Metals, mostly the boring gold, iron, aluminum, copper, and so forth, the ones that we can find in buildings and electric infrastructure and so on, and lots of other materials that are found in buildings and infrastructure as well. But now that I present this to you, I think maybe for some of you the question is, well, okay, so what? So we've got all these millions of tons of materials out there. What does that mean? Why is this important? Why would we bother counting all of these materials? So I'd actually like to take a step back, and I apologize for this, but maybe talk about some theory that explains why we would be interested in these things. And I would like to use the framework developed by Donella Meadows, a systems scientist, called the Means and Ends Framework. Maybe some of you have come across this before. You can see here from this report where it was presented originally. It's from 1998, so it's been out there for a while. And it supports sustainability science. And the major diagram inside this report is this triangle. So I would like to maybe spend a couple of minutes explaining what this triangle is, because it supports the work that I do, me and my colleagues that do socioeconomic metabolism research. So here's this triangle, and at the bottom we've got, well, not bottom, let's call it the base of the triangle. We have means, and at the top we have ends. Let's use, well, an example of a product, a simple one, phones. They are means of communication, right? The word means is already in there, in the title. They're everywhere. You probably have one of these, at least one of these in your pocket right now. And they are, well, in the end, they are composed of materials which come from the ground. Plastics, metals of all sorts and different sorts. Nearly half of the periodic table is actually in our phones nowadays. And these materials all come from nature, but of course they don't look and behave the same way that they are in nature as ores or raw materials. They go through a lot of industrial processing in order to become phones in the end, right? But they are physical things composed of all of these physical materials. But then the question is, what do we get from our phones? Well, it's a smartphone, so we get a lot of things out of it, but I guess the basic thing we get out of it is communication. That's the ends. So the phone is a means of communication in order to provide us with this service that we need for, well, communicating with each other. Using this same approach, we can ask, well, what about a house? A house is also built of materials, different materials, much more in bulk materials and in mass. And we can ask, what do we get from a house? There could be lots of different answers to that, right? I guess shelter, dwelling, a sense of security, right? A roof under our heads. But it's more than that. We also get, well, if we own the house, then it's something we own, right? It's wealth, a sense of ownership, maybe even social status, right? Because it's not just the house, it's also where and what it looks like and so forth. But so these are the ends for which the house exists, right? To provide us with these services. But it's actually not the end of this triangle. All of these services, societal services, are out there not as a final end, as an ultimate end. They are supposed to provide us with something beyond that, right? things like well-being or quality of life, a sense of satisfaction or success or self-fulfillment, very abstract things that we all strive to get, right? Those would be the ultimate ends. And then if we look at it that way, we can say that there is a structure here, right? The ultimate ends that we hope to achieve as a society, as human beings, is provided by these intermediate ends, by these services that we are looking for. And these in turn are provided by physical stuff, by our goods and products and buildings and so forth, which in turn are provided by nature from natural materials that we convert through industrial processes into these goods, right? So there is a link here between these ultimate means and these ultimate ends with the physical infrastructure and the built environment somewhere in the middle, providing these technical services and functions. That means that buildings, in this example, have a role to play in the link between nature and these ultimate societal ends. Of course, you could say that this is a very materialistic way of looking at things, right? Some people don't need physical stuff to provide these ultimate ends. That's very true. But when we ask what do we have that house for, that's where it fits into the framework here. And think about well, what if we don't have this nice American style house? What if we had this house instead? Well, on the one hand, obviously, just from looking at the picture here, it requires less materials, which might actually be good for the environment because, well, we would extract less materials, put less pressure on the environment. On the other hand, this house probably doesn't provide us with all of the services that we get from that previous house. So this meets ends less well than the previous example. And that means that those services, if we don't get enough of them, then maybe we are not as, our well-being or quality of life is not as good as compared to that previous house. So true, we did use less materials here, but maybe in the end, it doesn't fulfill the ends as much as we would hope to. And then we can do this example for other types of products and goods, such as a car. It's supposed to give us the service of mobility to get from place A to place B, transport. It's again wealth because we can sell it and get some money in return, social status, depending on the car that you own maybe. And we're supposed to, again, this is supposed to make us happy in the end and feel well. In reality, though, I think many of you would agree with me that it doesn't manage to fulfill all those ultimate ends in the end because there are a lot of things that obstruct it from doing so. So we own it, we hope to get these services, these intermediate ends, but in the end, we don't really, more often than not. So, but this way we can link these things and put each one of them in a different step in this pyramid. So what do we really get? How do we get these ultimate ends? That's a very open-ended question. But at least we have a framework to work with right now. And if we replace the product that provides us with the service of mobility, well, in this case, if we replace the car with an electric bicycle, maybe we consume less materials because it's much smaller than a car, less energy. But the question is, does it still provide us with the same services? Maybe some, yes. In the case of mobility, it actually gets us to work faster without being stuck in traffic. But maybe some ends like wealth, social status, well, that's questionable, right? It really depends on the person. So it becomes a bit more complex, but at least we have this hierarchy of how means connect to ends with these intermediaries in between. that can help us place things where in a way that there is a certain logic to it. And if we want to generalize this, then we could say that the ultimate means are the natural capital, which provide us with materials and energy for our built capital. And in return, that provides us with these services, which we sometimes measure as social capital. And then there's well-being, which I'm not sure if there is a good measure for that yet. So let's keep that with some question marks. But what we would like to ask then is, can we improve these things which are at the top of the pyramid? Can we improve humanity's well-being and the quality of life and so forth without requiring more and more of these ultimate means, the natural capital that involves all sorts of different, pollutions, wastes, and other environmental burdens? And this is where, from my perspective, this built capital, the intermediate means, the one that is here in red, that's where I focus on this question. Because this, by understanding the built capital, this helps us link between the environment and socioeconomy. So on the one hand, the environment, for building up our cities and products and goods, it requires huge amounts of extraction of materials and energy sources from the natural environment. It alters the landscape. It involves huge amounts of inefficiencies and wastes. The required materials and energy are huge and growing, and it also means that we produce more CO2 emissions and other greenhouse gases and other toxic materials, particulate matter, and other types of pollution. But then on the other hand, they are the ones who provide us with these societal services and functions. And they also serve as capital in economy. It's one of the basic means of production in economics. And the way in which we use them, right? It's not just the type of materials, but what they end up being, this type of house or the other type of the house, where they are located in the context of the bigger built-up capital of the city and the countries. They dictate lifestyles and life quality, not just from the material, but also from the design and the amount and their location and the quality of the product that ends up being constructed or fabricated from those raw materials. So this is how the built capital is actually an intermediary that connects between the environment and all of the pressures we put nowadays on the environment and the socio-economy. So now that we have this short introduction of why we would be interested in measuring the weight of the cities, let's go back to that title that I gave you in the beginning, Socioeconomic Metabolism. So what's that? Well, I'd like to focus on two words here, the economics and metabolism. First of all, economics. Some of you may be familiar with this definition of economics. It's one of many, but this definition says that economics is a science which studies human behavior as a relationship between ends and scarce means which have alternative uses. And I marked the word scarce means here because I would like to link it to planetary boundaries. The amounts of materials and energy that we use we're already, as humanity, we're already overstepping the amount of materials and the energy and other things that the planetary system, that the Earth provides us with. And if people were living with the same lifestyles as certain countries, as developed countries, we would need much more than one Earth to provide all of these basic means to support that type of lifestyle. And indeed, we have already, as a society, we've already overstepped some of the planetary boundaries of the various services that the planet supports us with. So this is a very, very extreme way of looking at the term of scarce means. There's a physical limitation. But then you can ask, so what kind of materials does humanity actually consume? And we've done a lot of extensive accounting to figure that out. This shows us 40 years of material consumption, which means the amount of materials that humanity extracts from the natural environment every year. And as you can see, and maybe it's pretty clear and not unsurprising, it's been growing from one year to the next. We've got updates. I should update the slide to more recent data. It keeps on growing, but you can also see here, we aggregated the materials into 4 basic categories here, and non-metallic minerals and materials ores, which are the major things that end up as our stuff, take up half of the materials that we take from the environment. The other 2 types, fossil fuels and biomass, most of them are used up for energy. Although, sure, some fossil fuels become plastics, some biomass becomes building materials or furniture and so forth, but the vast majority is for energy, to run our stuff, to give energy to our products and goods in the built environment. So if we note that I use the word consume here, in the same sense as the food that we consume, human beings or animals or whatever. And that links to the term metabolism. And this is the definition from the dictionary. Metabolism is the sum of the physical and chemical processes in an organism, a biological organism, that's what they assume, by which its material substance is produced, maintained, and destroyed, and by which energy is made available. But note how, instead of giving you here photos or pictures of how a biological organism does that, we've got pictures of how society does the same thing. So basically what we're saying here is that we're using the notion of metabolism to talk about society as an organism, the city as an organism, or the country, or the entire human society even. And then we can ask, well, so we've got all of these materials that are consumed by society from the environment. Are they all the same? And again, we can look at this from the metabolic perspective. Even the food that we humans, for instance, consume, there is not necessarily a direct relationship between the amounts of materials that we consume and what they give us. For instance, in this box of cereal, and most of our foods, we have these labels, right? And we can see in a portion of food consumed by a person, carbohydrates in this case are by far the biggest percentage in mass out of this type of food, 1 grams. But then vitamin C is 13 milligrams. So it's a tiny portion, but it doesn't imply that carbohydrates are more important than vitamins, right? And even if we look closer, vitamin D, it's 0.84 micrograms. So it's a tiny amount, but it's crucial for our well-being, right? So that's in the case of a human organism, an adult human organism. We can use this analogy for the materials that as well. So for instance, we have some materials that act more like the carbohydrates and proteins and maybe fats. These are materials that are mostly widely available and extracted locally. They are quite common in that sense. Economically, they are pretty cheap to purchase and also to produce. And they have high environmental impacts, mostly because of the sheer amounts that we use, because we use so much of them. And then on the other extreme end, maybe the equivalent to vitamins are some other materials that are not very common in nature. They tend to be monopolized by very few producers around the world, maybe even just 1 or 2. They are pretty expensive per unit. They have high per unit environmental impacts. So it's not the amounts that we use. It's even just extracting a few of them from the mine involves a lot of environmental impacts. and many countries deem them to be strategically important, to call them critical materials. So you could say that maybe they sort of act like modern society's vitamins. These are mostly precious metals, rare earth metals, and so forth. So by using these analogies, we can answer what is socioeconomic metabolism. One definition, recent definition, is that this is the analysis of the physical interaction between economy and nature and natural resources. So basically, we use this analogy to account for and look at the resources and the materials that we use, and ask what do we get in return from them, in a way that we can say, is this a healthy approach for consumption or not, and what can we do about it? One of my students joked that basically we are trying to be the dietitians of society. Maybe. I'm not sure if dietitians would be happy about this. I'm glad I'm presenting this to you today and not to the Department of Biotechnology and Food Engineering in the Technion. Not sure how they would take this. But this approach actually supports at least two of the Sustainable Development Goals directly, and a few of the other ones maybe indirectly. But within these goals from the United Nations, there are several goals and several indicators that are actually specifically related to this way of looking at consumption of materials and the way that we use them. Specifically in my own research, in recent years have been focusing on construction materials, which would belong to those bulk materials, more like carbs or protein. And maybe a question, if we keep using this metabolism analogy, is the question of whether they are muscle tissue or fat. And in which cases do they act as muscle tissue, as something that supports society, and in which cases they don't, or do so in an inefficient way. First of all, in order to answer this type of question, we need to, again, account for these materials, because nobody is doing this. Nobody knows exactly how many materials are out there. So it's up to us to, first of all, quantify how much there is. Of course, we can't put a scale under the city, and we don't want to wait for everything to be demolished in order to measure how much was there. We want to assess how much is there now. And in many cases, we do so by quantifying the data out of maps, sometimes historical maps. And I would like to show you one example that we recently published from China. This is a 10 square kilometer, well, they call it neighborhood. I guess in Israeli terms, it's a small city, but this is actually an industrial zone historically. And we extracted data and converted it into the mass of all of the materials in all of the buildings in this neighborhood or district, more accurately, over 100 years. Since it was founded in 1910, and you can see this is done in GIS, and we have the buildings here on the map. Blue is residential buildings, yellow means industrial buildings, warehouses, factories, and so forth. And we started tracking them over time. So you can see how this is the beginning, the founding of the district, and it starts growing and growing. This is immediately after World War II, and then it continued to grow very rapidly. It became one of the biggest and most important industrial zones in all of China. And you can see that by 1997, the area was basically filled up. It was saturated. One of my students with a background in the life sciences, in biology, said that it looks like a petri dish to him. So let's take a look at this again, how this place evolved. And you can see how it fills up with more and more buildings, which support the economy of China. And this is 1997, and it basically filled up, no more space. What do you think happened next? I'll give you a hint. Around that time, China had some, well, this was heavy industry, and China was transitioning to a different type of economy, and these factories were no longer supporting the economy of the country in the way they used to. Many of them are even closed down. So starting in the early 2000s, this area started changing quite dramatically. We've got hundreds of buildings here, and this is 2002. You start seeing these blue residential buildings in the sides here, towers, all of a sudden. And then 2004, 8, 2011, and our most recent snapshot is from 2018. In 15 years, this entire city was fully replaced from a huge industrial zone to a much huger residential area with the red one buildings are new here. They are commercial ones, offices, shopping centers, and so forth. And this is ongoing. And we asked ourselves, what happened here? This is urban renewal on a Chinese scale. How many materials were required for this? How many materials were needed, and how much construction and demolition waste was created through all of this? We can see here that it's not just that the number of buildings have changed, it's also the type of buildings and the way and the materials that they are constructed from. That's in the graph here to the right. So by having these snapshots of the extracted from maps and converted into materials, we could also identify the buildings that disappeared, became wastes, right? We assume that they became demolition waste. The buildings that appeared well, there was demand for these materials to come from somewhere, probably from mining and from extraction from the natural environment. So by doing this, we can also say how many materials were in demand and how much waste was created. And then we can even ask, in the same period of time, technically, could we have recycled the demolition waste and immediately on site convert it into recycled construction material? They didn't do that in this urban renewal project, but they are planning more and more of these. Can they reduce the demand for new virgin materials from the ground by reusing and recycling the materials that are already there? And it turns out that the answer is not quite, depending on the type of material. Not everything is 100% recyclable to start with, but the quantities and the type of material demands are different from those wastes as well. But it's not only that, but now that we know how long buildings existed, we can build up these survival curves and see what the lifespans of buildings were. And it turns out that buildings, especially the ones that were built in the 1990s, had a lifespan on average of less than 10 years. And well, a building that lasts for only 10 years, that's not very efficient, right? So there might be a missed opportunity there. But these are the types of questions that we can then look at once we have this type of data. And that means that we can ask these things, these questions that appear now on the screen. First of all, how to use the materials that we already stocked as buildings and infrastructure. How can we use them well? And what does well actually mean? We would like to ask how much material stock is sufficient. Is there a level where we can say this is enough and we can be living happily ever after without any more material requirements? Big question. And also how to reduce the new inflows from the environment and the outflows of wastes and emissions and pollution back to the environment caused by end-of-life materials. The work that I just showed you in China took, wait, I'm calculating here. It took 5 years since we started working on this, and until it got published. It involved a big number of students manually mapping these maps, georeferencing them, converting them into data, site visits to see what it looks like nowadays, and visits to old libraries to look at pictures, to make sure that we actually estimate the right type of stuff. It's very resource intensive to do this type of work, and it's great, but it's only one district in one city in one country. So lots of colleagues of ours do this kind of work for different cities around the world. And as time goes by, there are more and more of these studies, which is great because then we can start comparing them. But if we want to look at these big questions that are here on the screen, we need data for the entire world. And in order to do that, in my research group at the IDC, and with colleagues from around the world, we have been working on developing other methods to estimate the material stocks. Specifically for large scale, global scale remote sensing is the way to go. And one of the promising approaches in this regard is this type of data set of the lights emitted at night across the world. Of course, the picture that we see here now is not a real picture, obviously, because the Earth cannot be all dark all at once, right? So this is stitched up. The satellites take pictures of different locations around the world. Scientists stitch them up and combine them together. They remove noise and remove things like natural lights, like volcanoes and lightning. They remove things like boats and ships and sporting events that happen only now and then. So we only have the permanent or the long-term lights. And then we assume that wherever there are lights, there are also buildings and cities and human activity. And we would like to convert that into how much mass of materials is out there in each of these dots. And we have been developing this for quite a while now. We recently published a first estimate. The approach that we use is that we've got these cities or settlements all over. This is an exemplary city in Europe. If you recognize which capital city this is, you get a thumbs up. But if it's too hard to recognize with regular satellite imagery, let's take a look at what it looks like in nighttime lights. This is what it looks like. And as you can see, we don't really see buildings anymore. We see these blobs of light emitted from city centers. And there's more than one of those. And we actually exploit that and convert that into units of different settlements with their own lights surrounded by less lights. And we call these cells because maybe they look a bit like biological cells. You see there's a nucleus and surrounding material around these cells. So we identify, we have algorithms that identify these cells of activity of light from the satellite data, and we then convert that into the overall how many buildings are represented by that light. Of course, that depends from and changes from one place to the other. The relationship between lights and buildings is not stable across different locations. So we've got algorithms detecting what the relationship should be. And this is the end result of the published work for the entirety of Europe. And we see here that there's lots of material stocks, first of all, but they're not evenly spread out. Maybe that's expected. But even in different cities, the way the spatial distribution of the material stock behaves is very different. For instance, places like Paris and London have very big, very high material stocks in a centralized location, and around them there is not much, relatively speaking. But other places like Milano in Italy, but also other places in the Netherlands and in North England, there are smaller city centers, but the spatial distribution of the material stock is much wider. And then there are places like Warsaw and Berlin that have these relatively small centers, but they have these bespoke like lines emitted out of them, like a sunburst type of distribution of the material stock around these city centers. So all over the continent, there are very different types of accumulations of material stocks. We can also aggregate these results to the country level on the left-hand side and to sub-national administrative regions on the right-hand side. And then we can start asking very interesting questions that we weren't able to ask before, such as, what do we get from all of these materials now that we have data for the entire continent? Are some cities more similar to others? Are some cities, do they use their materials better to get, well, better something? And this is what we are working on right now. And the next slide that I'll show you is a work in progress, just from last week. And this is the population density of cities, not our results. This is from the statistical offices of the European Union, compared to how much materials per person exist in those cities. And it turns out that we can cluster these and find that there are some certain patterns, and especially the blue ones are interesting. These are big cities, mostly capital cities, as you can see here, that have very, very high population densities and very low, relatively speaking, materials per person, which means that they use the materials that they already have in a much more efficient way. They need less materials to provide the same or even better services to the people that live in those cities. And then there are the orange ones, which also have low materials per person overall, mostly, but their population densities are not as high. You can see here Berlin, Napoli, Vienna, Madrid, and so forth. And lots of other cities, the vast majority of smaller cities and villages and towns and settlements that have a very big range of building materials per person. Some of them have very high amounts of materials per person. And now we're trying to figure out, especially for the red group, the red cluster, what's going on in those cities? Why do they have so much material and so few people? What's going on there? The size of the circles here are the number of people in absolute terms that live in those cities. So this is just the beginning. We're also now adding to this things like the economic productivity of those cities, things like life expectancy, education levels, and lots of other socioeconomic factors that would explain the well-being in those cities. And we want to see whether the material stocks are used efficiently to provide us with all these services, and then also to look at the impacts, the environmental and sustainability impacts involved with building up these cities in their different structures and the way in which materials are used there. But we do this not only to look at what is happening now or happened in the past, like the Chinese example, but also to look at the future. What could happen in the future? Instead of trying to predict, which is very tough and prone to, failure, we create different scenarios. And one of our recent projects in this regard is an international collaboration that we did for the United Nations Environment Program, in which we looked at different countries, starting from the G7 countries and India and Europe, and India and China, and looking into their potential futures, not just one future, but parallel universes in which they go in different directions, with more environmental awareness, with less environmental awareness. And we wanted to see how many emissions, greenhouse gas emissions, they are going to emit from their buildings from now until 2050. And also, if we start implementing different strategies and different opportunities for efficiency measures in the way in which buildings use materials, how many emissions can we reduce thanks to that? So we looked at a big set of different types of strategies, which what they have, all of them have in common is that the idea is to have at least the societal services that we would like to have, say number of houses or floor space per capita, but using less materials to obtain those services. So there are lots of different strategies here. I'll just mention a few. Some of them are technological or related to engineering, like lightweighting our buildings or using less material by design. So we still get the same building, the same service, but with less materials. Other solutions are regarding design and social trends, like downsizing, just getting used to living comfortably in smaller houses, for example, or more intensive use of the houses that we have and we will have in the future. And things like things that might be related to both policy and technology, involving how we reuse the materials that we already have and making a transition from not just recycling, but to look at the built environment as a mine, as the mines of the future, and considering them in the same way that we look at mines nowadays. Turns out that it might actually be quite valuable. Some materials are already more highly available or easier to obtain from the built environment if we mine it when these buildings and infrastructure and products reach their end of life, then it would be from getting them from the environment, from traditional mining and extraction. So we combined all of these strategies. We wanted to see first, if we implement all of them, how many emissions of greenhouse gases can we reduce from the production of these buildings and from using them, you know, the energy for heating or cooling and so forth. And also the different contributions of these different types of strategies. Turns out that by far the most efficient or the most influential strategy is more intensive use of the buildings that we already have. And the other strategies also have a lot of influence, especially recycling and material recovery, not just from end of life, but also during the production phases. So less waste in the factory floor. And there's actually substantial reductions of greenhouse gas emissions in the future that can be obtained with these by implementing these strategies. In the G7 countries, the reductions, if we start building up the right frameworks of policy and economics and habits and so forth to do these strategies, by 2050, we could reduce a further 35% in the emissions of greenhouse gases. And in places that are still developing, like China and India, the potentials are even higher. 60% reductions of greenhouse gas emissions by 2050 can be obtained by implementing these material efficiency strategies. The reason for this, they haven't built up their stock yet. So they have more opportunities to get it right compared to developed countries if they start implementing these strategies right now. So, yeah.
We have only 10 minutes more or less for questions or comments. Right. So,
yeah.
Okay.
So, yeah. So we're working on developing these further, including for Israeli case studies. But this is my last slide. I hope I gave you a good idea of what socioeconomic metabolism is. There are lots of open questions. Many of them involve exactly what are those good things that we get out of these stocks of products and buildings and so forth. Well, it's getting more and more common in sustainability circles. In Israel, it's still just a handful of people, but it's growing even here in Israel as well. So that's about it. Thank you very much for listening. And I will be happy to take your questions and comments.
Thank you, Tomer. I guess that we have here mainly architects, so probably they have something to say regarding your the questions you raised. So questions, if you have.
I have one question. Oh.
Clear?
Yeah. Thank you for your lecture. It was really amazing seeing like the visualization of the mass sorted by city. What I wanted just to clarify, how did you manage to quantify like the mass of built up of building materials? And does the mapping include also underground material? And can you use photogrammetric measurements or tools to reach the same measurement?
Yeah, great questions. So the first question was, how did we do this? There are multiple approaches that we had to do, but basically they involve archetypes of buildings that we empirically measured how much materials are in there, say by following their construction or following their demolition and recording how many materials were involved, and making estimations on existing buildings to assume or estimate how much materials we think are in those similar buildings. There are lots of uncertainties involved, and part of the fun here is to also estimate the level of uncertainty and what do we know and what we don't know. These estimates also include the underground parts, foundations, and other underground components of buildings, substructures, and so forth. Sometimes it's very interesting to separate those. Some of the underground stuff is not going to get recovered. It's going to stay in the ground even after demolition. So those materials might actually be lost in a sense. And your third question was about, no, I forgot your third question.
Photogrammetric measurement.
Oh yeah, So we are constantly trying to improve these methods. You could see that the polygons there were simple rectangles. And then it's sometimes it ends up being two practical questions. One is that type of data available. In many cases, the answer is unfortunately no. And two, by how much does it improve our estimations? So there's a trade-off of the extra computational power required. And if we get, well, good enough estimations with simpler methods, then we need to do these trade-offs and figure out what's the right approach. Say for the Ministry of the Environment, when they want to know just how many millions or billions of tons of construction materials they will have to deal with for as waste, they don't really care about those relatively small changes from increased data reliability. So they wouldn't support, they wouldn't fund us for that, unfortunately.
Thank you.
Thank you. Great questions.
More questions? I would like to ask something related to the population.
Yeah.
You assume that the population will keep growing more or less as it is growing the last years, I guess. Or not? I think this is a key question. What do you assume regarding that?
Sorry, you were frozen for a second. Did you
sorry.
ask whether the assumption is that the population will keep increasing?
This is my question.
Yeah, so we take the forecasts or predictions from statistical bureaus, for example, and we try to use the different variations in those to see by how much that would affect the results. And of course, it's a case-by-case basis. For a country like Israel, we do assume that there will be a population increase. The question is how much. For countries like Japan, the forecasts are negative. So we take that into account, and they actually end up with too much stuff, too many buildings, empty buildings. And we need to figure out what to do with those. So it's really a case-by-case kind of question.
Okay. More questions? יש עוד שאלות? טוב, אני מניח שחלק גדול מהאנשים, או חלק מהאנשים שכבר יוצאים, הולכים למקומות אחרים, אז אני מודה לך, תומר, אני מפסיק את ההקלטה, אז תודה רבה.